So our next topic in chapter 11 is graphing ellipses. This is so similar, and we're building up these ideas from circles. So again, we're going to graph an ellipse in standard form using the center and the vertices. We're going to write an equation of a given ellipse. We're going to find the foci using the formula. And of course, we're going to complete the square to find the center, foci, and vertices. So our first goal is to graph an ellipse in standard form using the center and the vertices. So all ellipses have equations that can be rewritten in the standard form. Now notice that what's changed here from the circle is it looks like we divided through by r. And the reason I say that is because on the right side it looks like we divided through by r squared, and that gives us a 1 over there. And then we did something interesting. Where the r squareds would have been in the two denominators, if we divide through by r squared, we get two different numbers, a and b. And those are kind of like the horizontal radius and the vertical radius. Horizontal for x, remember that's a left and right dimension, and vertical for y, that's an up and down dimension. Notice that hk is still our center, but our new a and b, taking the place of that radius, are our offsets. Offsets just tell us how to make that rectangle that the ellipse lives in. In other words, how we get from the center to those vertices. So let's take a look at an example. So here's an example. This is in standard form, x minus 5 quantity squared. So we know that 5 is h, that is the x-coordinate of the center. We look at the other numerator, y minus 2 quantity squared. We know that the k value, that is the y-coordinate of the center, is 2. So we've got the center, 5, 2, and we then look at what else we've got. Now we're interested in those offsets. The horizontal offset is a, that's the square root of 4, or 2. The vertical offset is b, that's the square root of 9, or 3. So let's now plot this. We know that the center is 5, 2, and we know that in exactly the same way that we found that for circles. And we derived that from the Pythagorean theorem. So we plot our center. You've got to start by plotting the center. The offsets are no use to you if you don't know what they're offset from. Now from that center, so in our next step, when we're using the center and the offsets, from that center we go up 3 and down 3. Remember, the vertical offset b is 3. So from the center, we're going 3 units up, and we're going 3 units down. And that finds 2 of our vertices. Notice that in both of those cases, x is 5. But we add 3 to y, 2 plus 3 is 5. We subtract 3 from 2, and we get negative 1. So that gives us 2 up and down vertices. Now we do the exact same thing with a. A is 2. So that tells us in the horizontal direction. And this is easy to remember. You don't have to remember a and b. Remember that 4 came from the x term. So anything that came from that x term is telling us about right and left. So that tells us that we're going 2 units to the right, 2 units to the left from our center. We found the center first. So now x values are changing, but y aren't. The y is 2 in all 3 cases, but we're adding 2 to the 5 to get 7, and we're subtracting 2 from 5 to get 3. In other words, we're going 2 units to the right and 2 units to the left. Now the next step is to draw the representative rectangle, and this is a great way to draw ellipses by hand well. It's also foreshadowing what we're going to be doing with hyperbolas in the next section. So it's important to do this for lots of reasons. Now notice that I say draw the representative rectangle, and then I say sketch the ellipse. And the reason I'm saying that is we can be really precise with our representative rectangle. If you were taking this class with paper and pencil, I would look at your representative rectangle and I'd see that it went through those 4 vertices perfectly. I'd also see that you probably did your best job to sketch. That is, not exactly, but pretty darn close to sketch that ellipse. And I think you'll find that when you have the representative rectangle, it really helps to sketch the ellipse, just like it really helped to sketch the circle. And the reason's the same. That ellipse is tangent to the representative rectangle at each of these vertices. That is, just for a moment at 7,2, the ellipse is vertical. It just touches down and then takes off again. It just touches like you're inflating a balloon inside of a rectangle, just touching those sides. Now, the next 2 questions ask us to graph, and the way we do that is we tease out the information that we're given in the equation. So in this first example, let's find HK. Let's find our center first. Notice that we're adding. That means that we're actually subtracting -2. H is -2. I look over in the y term and I see subtraction. That tells me that K is 1. Our center is -2, 1. Now let's talk about our offsets. In the x direction, that is right and left, we're going to go 3, that is the square root of 9. And in the y direction, we're going to go 5, that is the square root of 25. Okay, so let's graph this. First off, we know that it's an ellipse, so let's talk about that. Our h, that is the x-coordinate of the center, is -2, so let's make our h into -2. K, that is our y-coordinate of the center, is +1, so let's make K into +1. And now let's deal with our offsets. So A is the denominator down there. The square root of 9 is 3, so we want A to be 3. And B, the square root of 25, is 5, so we want B to be 5. Now this is showing us a lot of useful things. It's showing us the center, it's showing us the 4 vertices, it's showing us the representative rectangle, and it's also showing us 2 foci, which are denoted F sub E1 and F sub E2, foci. Okay, now let's do the same thing with this second equation. Let's first ask the question, what is HK? When I look inside the numerator of the x term, if I wanted to, I could think of that as x minus 0. So h is 0. K, remember, is the result of performing subtraction, so k is -1. Our center is 0, -1. Now let's look at the offsets. In the x direction, downstairs we've got a 4. The square root of 4 is 2. So we're going to go 2 to the right and 2 to the left from the center. Notice that we don't have a denominator under the y squared plus 1, which means that if we needed a denominator down there, if we needed 1, it would be 1. So b is 1. So let's take that information and graph it. So here's the graph of the previous ellipse, and let's change it as we need it. Remember, h is 0, so we're going to drag that over to 0. K is -1, so we're going to make K into -1. A is 2, so I'm going to make A into 2. And B is 1. So there's our ellipse. We could zoom in and take a look at it. It's also showing us the foci, those 2 blue dots. There's our ellipse, the representative rectangle, the vertices, and the center. Okay, the next goal for us is to write the equation of a given ellipse. So here we're given an ellipse and we're asked to find its equation. And we're going to work through this exactly the way you'd expect. We're going to pick out the information from the graph and then plug it into the equation for an ellipse in standard form. So the first thing that I see is that the center of this ellipse is at x equals -2 and y equals 0. So we've got our center. Now we need our offsets A and B. A is the horizontal offset, that is right and left. It looks like we're going 1 unit to the right, 1 unit to the left from the center. So A equals 1. B is our vertical offset, that is up and down. It looks like we're going 2 units up and 2 units down to get to our vertices. So now we've got H, K, A, and B, and we plug it in. So into the standard form it goes. Now we can clean this up. Just like in the previous example, you don't need to show a denominator when it's 1, and you don't need to show subtraction when you're subtracting 0. So let's do a little arithmetic there, and we get a nicer form. Let's take a look at this second ellipse. It's given to us. We've got its center. The center is at x equals 3, y equals 4, so we know h and k already. Now we need to count out the horizontal and the vertical offsets. So from the center, we're going to count over to that vertice on the right. So 1, 2, 3, 4, 5. So it looks like A equals 5. And now we're going to do the same thing for our vertical offset. We're going to count from the center to our vertice up and down. So let's go 1, 2, 3, 4 to get to that vertice down there. So B equals 4. Now we're going to plug this into the standard form. So we've got in the numerator an x minus 3 quantity squared. Downstairs, 5 squared is 25. In the second term, the y term, we've got y minus 4 quantity squared. And of course, b squared, 4 squared is 16. All still equal to 1. This is an ellipse. That GeoGebra file that we've been using has been graphing the foci for us. That's the plural of focus. There are 2 of them. When the planets orbit the sun is at one focus of the planet's elliptical orbits. The elliptical orbits also precess, which makes it a little bit more interesting, but that's a really good approximation. You can say that the sun is at one focus and that the orbits of the planets are ellipses. So an ellipse can be drawn with a string attached to 2 fixed points called the foci. That's a very physical way of thinking of this, and I really want you to see that. When I teach this concept in class, when we used to have chalkboards, I had this piece of wood that one of my colleagues made with 2 little door handles that looked like at either end. Those were the foci, and a piece of string made into a loop, and I'd grab one part of that loop and I'd hold it taut, and you could draw a really good ellipse on the board just by using that. So this means that the sum of the distances, d1 and d2, are the same for any point on the ellipse. So here's 2 examples. We'll look at a GeoGebra file in a second. But for now, the 2 distances, that is the distance from the point to one foci and the distance from the same point to the other foci, add to the same amount. So for this ellipse, that constant distance is always 7.55. Let's look at a GeoGebra file for this. So here's the exact same GeoGebra file that I made to make those 2 illustrations in your workbook. So let's drag that point around. And as we drag it around, notice that those 2 distances do change. They're always changing. But that sum, when we add them up, is always the same. So you can imagine a piece of string that is sometimes forming D1 and other times D2, just kind of holding that taut against those 2 foci. And you can see it sweeping out that ellipse, always having the same sum. Here's another GeoGebra file that shows that exact same process being animated. Here, the sum of those 2 distances is k, so the length of that piece of string connecting each focus to the other is 10 units long. And you can see the ellipse that it is sweeping out as we pull that piece of chalk taut against those 2 foci. Now there's a lot of ways to make this next concept way more complicated than it needs to be. This is also a topic in pre-calculus, as virtually everything in algebra and trig and geometry is. And there's so many ways to make this complicated that I'm going to completely avoid a huge number of discussions and simply make a single statement. And that is, the foci lie on the longer axis. So whichever of those 2 offsets is bigger, that's where the foci are. In other words, we're going to find the foci by finding a new offset. We're going to call that offset C. Remember, A and B are already our horizontal and vertical offsets. C is going to be the offset that lets us find the foci, but it's always on the longer axis. And the moment that you take that and say, okay, the moment I see C, I'm going to use C in whatever offset is bigger, the longer axis, you'll be fine. So let me show you both of these cases. And the moment you've got this, you don't need to worry about anything else. So in our first case, A is bigger than B. There's the algebraic way of saying it. Notice that I show that same situation with the arrows that I have. That is the offsets from the center. That was the way I was showing this before. So the center, of course, is the point in the middle. Those arrows are the offsets. And A is bigger than B here. The horizontal offsets are bigger than the vertical offset. So in this case, the foci are, well, they lie on the longer axis. So if our horizontal offsets are the bigger ones, then to find the foci, we go C to the right and C to the left. In other words, C is itself an offset, but it's always in the direction of the longer axis. Now, here's the formula to find it. So that's geometrically where it lives. To find it, we simply say, let's take the differences of those squares of the two offsets, a squared and b squared. Now here, a squared is bigger than b squared because a is bigger than b. So if we want to take the square root of a positive number, we better do the subtraction in this order. Now that helps because notice that our formula when b is bigger than a is different. And so you might say, oh goodness, this is going to be a lot to memorize, but it isn't. If you're going to find AC by taking a square root, you better be taking the square root of a positive number, that is bigger minus smaller. And notice that that's exactly what we've got in this second case. In this second case, B is the bigger of the two, A is the smaller one. And I've shown that also geometrically. Notice that in this illustration from the center, we go up and down more than we go right and left. They have a larger magnitude. So what does that tell us? That tells us that B, that is the vertical offset, is the bigger of the two. So to find the foci, we use C in the, and I'm going to say it again, the foci lie on the longer axis. Here, the up and down axis given to us with B is the bigger one. So we go up C to find that first focus. We go down C units to find the second. Now, that's certainly one way of showing it, but sometimes mathematics is a little bit easier when you kind of mix in words. So here's the way I think of it. The offset to the foci is always on the longer axis, and always, that offset C, is the square root of the difference. Larger squared minus smaller squared. Well, of course it's going to be. You're going to be taking the square root, and you want a real number C. Okay, on the next page, it looks like we're asked for everything. The foci, a graph. We want the center, the vertices, and the foci to be plotted. And then we're given an equation that is not in standard form. I don't see any fractions. I don't see that equal to 1. So let's work through this. First off, notice that the x squared term doesn't have a corresponding linear term. There's just 25x squared, while the y squared term does have a corresponding linear term, that is negative 40. So we're going to have to complete the square on y, but we're not going to have to do anything with x at the moment. So notice first off that we can't complete the square with a coefficient, and if you go back to chapter 6, you can remind yourself that the first step was to get rid of that coefficient. We're not going to get rid of it by division, we're going to get rid of it by factoring. So let's factor out that 4 from the 4y squared and the 40. Now, when we do that, that leaves us a negative 10y behind. So that negative 10 is our m. That's the thing that we're going to go through and take half of. That's negative 5 and square it. And when we square negative 5, we get 25. That's the square that we're adding to both sides. Wait, hold on a second. We're not adding 25 to both sides. Notice that that 25 is inside of parentheses. It's being multiplied by 4. So if we're really adding 4 times 25 to the left side, we need to be adding 4 times 25 to the right side. So make sure you see that. We can factor that 4 out, and that tells us what m is, the negative 10. Half of that, negative 5. Negative 5 squared is 25, but we're not really adding 25 to both sides because it's in parentheses. Now, we've got a 100 on the right side, and that's great. But we're supposed to have a 1 over there. And that's the way I do these because it tells you how to do the arithmetic. You could look at the least common multiple of 25 and 4. That's another way to do this. But I simply look at the right side over there and I say 100. That 100 is supposed to be a 1. So we're going to divide through by 100. So in the next step, you can see that everything is being divided by 100. Our goal is to get a 1 on the right side. Now, notice that a lot of simplification is going to happen. And that's because the way I write these, the a and the b, that is the horizontal and the vertical asymptotes, are always integers. So let's take a look at the x term. And notice that 25 over 100 gives us a 4 downstairs. So when we simplify that first term, that x term, we're going to see a 4 downstairs. Notice that in the second term, 4 over 100, that simplifies with a 25 downstairs. And of course, this is equal to 1. So we've now got it in standard form. We can see that h is 0, k is 5, a is 2, and b is 5. So that tells us all sorts of good information, especially if we factor those denominators so you can see a and b literally. Now here, b is bigger than a, so when we're asked for the foci, we're going to use the formula where we take the square root of the difference of the squares with the bigger one first. So this is b squared minus a squared, or you can just simply think of it as larger squared minus smaller squared. 25, it comes from the 5 squared, 4 comes from the 2 squared, and this simplifies as the square root of 21, approximately 4.58. Now c is an offset, so it will tell you the distance that you have to go in the longer axis. Remember, the longer axis here is our b offset, so that tells us that we're going to go 4.5 units, or 4.6 or 4.58, depending on how accurately our scale is, drawn up and down. So let's take a look at that. Okay, so the first thing that we see is that h equals 0, so h equals 0, we're still graphing an ellipse. K equals 5, so let's drag that out to k equals 5. A equals 2, good, and B equals 5. So there's our ellipse. It's also showing us our foci, our center, our vertices, all sorts of good things. The center up there at x equals 0, y equals 5. The horizontal offsets 2, taking us to our left and right vertices. The vertical offset 5, taking us 5 units up from the center and 5 units down. And then the foci, about 4.58 units up from the center. That's really close to that vertex. And 4.58 units down.